KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss first one example problem based on the information we discussed in our previous classes, and then we are going to discuss one small topic, that is combination of thin lenses in contact. Combination of thin lenses in contact. Okay, right. So first we will see the example problem. I will read the problem first. Try to understand the problem. See here, if small f is equal to 0.5 meters for a glass lens, what is the power of the lens? Next, second one, three things are there to calculate or to find. So first one is over. Second one, the radii of curvature of the faces of a double convex lens are 10 centimeter and 15 centimeter. Full stop. Its focal length is 12 centimeters. Full stop. What is the refractive index of the glass? So by giving radii of curvature for double convex lens and then giving focal length, asking to calculate refractive index of a glass. Next, third one, a convex lens has 20 centimeter. A convex lens has 20 centimeter focal length in air. Full stop. What is the focal length in water? What is the focal length in water? See here, in the bracket they have given refractive index of air water 1.33, refractive index of air glass is 1.5. Okay, right. So in this example problem, he is asking to find three things, right? So in that first thing, he is asking to calculate the power of the lens. In the second one, asking to find the refractive index of a glass, and third one, asking to find focal length in water. Focal length in water. Okay, right. So one by one I will explain you. See here, solution. First, so in our previous class, you know that power is the inverse of focal length. So as much as clear, they have given focal length here. It is 0.5 meters. Asking to find power. So power is equal to 1 by f. Already they have given in meters. That's why, right? So it will be +2 diopter. Power is equal to 1 by f. It is +2 diopter. Next, second one here. First they have given some values. That is what focal length, radii of curvature. So that we have to write. Afterwards, you have to substitute in that given, known formula, that is lens maker's formula, along with sign convention. That is 1 by f is equal to, the formula is 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. That is the lens maker's formula. So in that formula, we have to substitute the given values, right, including the sign convention, Cartesian sign convention. Then 1 by 12 is equal to n minus 1 into 1 by 10 minus 1 by minus 15. So by solving this equation mathematically, you will get it as n is equal to 1.5. The refractive index of glass became as 1.5. Okay, right. Next, third one. See here, for a glass lengths in air, N2 is equal to 1.5, N1 is equal to 1, F is equal to plus 20 centimeters according to the given information, right? So from all these things we can write from length formula. From length formula we can write it as 1 by 20 is equal to 0.5 into 1 by R1 minus 1 by R2. So how we got 0.5 here? It is N2 minus N1. N2 minus N1, right? So 1 by F is equal to N2 minus N1 into 1 by R1 minus 1 by R2. So this is one equation. So we put as equation number 1. Now next the same procedure we are going to apply for glass lens in water. Glass lens in water. There N2 is equal to 1.5 and N1 is equal to 1.33. So that we are getting some other equation, that is what? So therefore 1.33 by F. 1.33 by F is equal to 1.5 minus 1.33. 1.5 minus 1.33 into 1 by R1 minus 1 by R2. 1 by R1 minus 1 by R2. So that is like equation number 2. Equation number 2, right? So finally from these two equations, so equation 1 and equation 2 we are going to combine mathematically so that we can find focal length, right? So that is what focal length in water, that is plus 78.2 centimeters, plus 78.2 centimeters, right? So in this example problem, in first they have given focal length asking to find power. Secondly, they have given radii of curvature and focal length asking to find refractive index of glass. Refractive index of glass. Afterwards, they have given focal length in air for convex lens and asking focal length in water, right? So in the bracket they also given refractive index of air water, that is 1.33, comma refractive index of air glass, it is 1.5. Okay. So based on this given information you can find whatever they are asking to find. Okay. So in first case power is inverse of focal length, as simple as such. So it will give us 1 by 0.5 means plus 2, it is diopter. Similarly in the second case, based on the given values we are going to consider the formula 1 by F is equal to n minus 1 into 1 by R1 minus 1 by R2, lens maker's formula, so that you can find n is equal to 1.5. Refractive index, whatever he is asking, that is refractive index of glass, we found as n is equal to 1.5. Next, for a glass lens in air, so based on the given values we are getting one equation, that is what equation number 1. Similarly, the same procedure we are going to apply for glass lens in water, so that it will give us some other equation. So by solving equation 1 and 2, combining equations 1 and 2, we will find focal length is equal to plus 78.2 centimeter. 78.2 centimeter, right? Now we are going to discuss the continuation topic, that is combination of thin lenses in contact. Combination of thin lenses in contact. Okay, right. So this topic help us to obtain desired magnification. To obtain desired magnification. For example, there is some living organism, small living organism like bacteria, right, virus, but I want to magnify that image. I want to see that object, either it is living being or some other. These many times, for example 10 times I want to magnify, 20 times I want to magnify, 100 times I want to magnify. So this is our requirement. So based on this, to achieve desired magnification, how many times you want to magnify, it is not matter here. Just how many times you want to magnify, no problem. 1,000 times also if you want you can magnify. But what helps us? regarding to our topic, that is what lens topic. So what can we do? Yes, we can do. So by taking a lens of different, for example, thin lenses, by taking 2 lens, by taking 3 lens, by taking 100 lens, right, you can achieve the desired magnification. So achieving of desired magnification according to our requirement is possible because of combination of lenses. So here combination of thin lenses in contact. Okay, right. See here, consider 2 lenses. Consider 2 lenses, right? Here A and B. Consider 2 lenses of A and B of focal length f1 and f2, right? So it is A, it is B. The focal length of A is f1, focal length of B is f2, placed in contact with each other. Placed in contact with each other. Let the object be placed at point O. This is the position of the object. At point O, beyond the focus of the first lens. Beyond the focus of the first lens, produces an image at I1. See here, produces an image at I1. Since the image I1 is real, it serves as a virtual object for the second lens B. Right? Afterwards, producing the final image at I. By acting this image I1 as a virtual object for second lens, final image will be formed at I. Next, formation of image by the first lens is facilitate us to determine the position of the final image, right? Formation of image by the first lens, right, facilitates us to determine the position of the final image. Next, in fact, the direction of rays emerging from the first lens, gets modified according to the angle at which they strikes the second lens. Okay, right. Assume that the optical centers of the lenses coincide due to thin lenses, because here we consider thin lens, no, that's why, because of thickness is very small. So you can assume that the optic centers of both the lenses coincide each other. Okay, then you can go for derivation step by step, right? Before going to get the derivation, once again you just see this information what I have written here along with the picture. You just try to understand what's happening in the picture. O is the object, AB are the 2 different thin lenses having focal length f1 and f2. After that, first, because of lens A, regarding the object O on principal axis, 2 rays are coming, right? So these 2 rays will form an image at I1. I am talking about only lens A. Now I am talking about only lens A. So because of lens A, the image is formed at I1 because of 2 light rays, according to our picture, according to our ray diagram, because of 2 light rays which are coming from O, from object, right? The image is formed at I1. Next, this image is real, but this image will act as a virtual object to the B lens, that is the second lens, to the B lens. So the rays which are coming from this virtual object will form a final image, is at I, right? So regarding this ray diagram and regarding the information or the situation, practical situation, the final image is I only, but how the final image is formed because of due to these 2 lenses is the interesting thing, is the important thing also, right? So object is at O only, but final image is formed at I due to the 2 thin lenses, due to the two thin lenses. Okay, so that is important here. Suppose if there is only one lens, our discussion will deviate, right? Because of having two lenses, the final image is formed at I, right? First image is formed at I1, right? That is because of first lens, that is A. Because of second lens B, or for the second lens B, this image I1 acts as a virtual object, right? So this second lens B formed image at I for I1 as a virtual object, I1 as a virtual object. Okay, right. So this is the reason and this is the situation happens because of two lenses in contact, right? And as we know already, it is the object distance of object from optic center. See the red light, that is the optic center, right? So because of thickness is very small regarding these two lenses, we assumed that the optical centers of two lenses coincide each other, right? And V1 is the image distance, but V1 is the image distance regarding lens A or first lens, but final image is I, no? Final image is I. So here the image distance is actually V. So with respect to two lenses A and B, the image distance is V. With respect to one lens, single lens, that is A lens, the image distance is V dash. Okay, right. So that only he is writing here very clear. Consider two lenses of A and B of focal length f1 and f2 placed in contact with each other. Let the object be placed at O beyond the focus of the first lens. The first lens produces an image at I1. Since image I1 is real, it serves as a virtual object for the second lens B, producing final image at I, right? Next, formation of image by the first lens is facilitated us to determine the position of the final image. In fact, the direction of rays emerging from the first lens, modified according to the angle at which they strikes the second surface, second lens, surface of the, curved surface of the second lens, right? That is one thing. And we are assuming that the optical centers of the lenses coincide due to thin lens, right? So that is the assumption. Next, now we are going for derivation. See this, observe carefully. For the image formed by the first lens A, we get, so actually the formula is, lens formula is 1 by V minus 1 by U is equal to 1 by F. Okay, so from that you can write 1 by V1 minus 1 by U is equal to 1 by F1. So here you just observe only the first lens, only the lens A. Okay, right. Next, similarly, so it is like equation number 1. We assumed as equation number 1. Next, for the image formed by the second lens B, we get, right? So for the second lens, this is the object, virtual object. This is the image. So here 1 by, same formula, that is lens formula, 1 by V minus 1 by U is equal to 1 by F. So here 1 by V means this one, it is the image distance, and U means this is. So this one acts as a object, virtual object to the second lens. That's why 1 by V minus 1 by U. See this, 1 by V minus 1 by V1 is equal to 1 by F2. 1 by F2, it is the equation number 2. It is the equation number 2. Only one formula, one formula, 1 by V minus 1 by U is equal to 1 by F. First we applied for first lens and then we applied for second lens, so that we are getting two equations, equation 1 and equation 2, right? Okay. Now adding equations 1 and 2, adding equations 1 and 2 mathematically, right? So we are adding equations 1 and 2 mathematically, so that 1 by V minus 1 by U, observe carefully, these two will get cancel each other, these two will get cancel each other, so that 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2, 1 by F1 plus 1 by F2, right? If the two lens system is regarded as, if the two lens system is regarded as equivalent to a single lens of focal length f. Suppose for example here we have two lenses, suppose if there is only one lens, then what happens? It is 1 by f, no? So that you can write 1 by V minus 1 by U is equal to 1 by f, right? So by comparing this equation, see the light, by comparing this equation and this one, that is what 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2, and 1 by V minus 1 by U is equal to 1 by F. We will get it as 1 by F is equal to 1 by F1 plus 1 by F2, 1 by F1 plus 1 by F2. It is the final equation we are getting for the combination of two thin lenses having focal length F1 and F2. So 1 by F is equal to 1 by F1 plus 1 by F2. Okay, right. But you can extend this equation for n number of lenses. Why not? Suppose if we have three lenses, you can write like this: 1 by F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 plus dash dash dash. So okay, if we have three lenses, we need to stop here. Suppose if we have more than three, that is the reason we put plus dash dash dash, right? So you can write it as plus dash 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 plus 1 by Fn, right? So sigma I is equal to 1 to n, sigma I is equal to 1 to n, 1 by Fi, 1 by Fi will give you final, I mean the resultant focal length, okay. Suppose if you want F, it will be reverse. For example here, if you do that, what is sigma I is equal to 1 to n, right? Sigma I is equal to 1 to n, 1 by Fi, you will get 1 by F. So by reversing that, right, you will get F value, that is the resultant or equivalent focal length of the combination of lens, right? So this expression, what my intention here is, this expression is not only for two lenses. For example, we took two lenses and we derived an expression for the combination of focal length, that is what 1 by F is equal to 1 by F1 plus 1 by F2. This you can extend for any number of lenses, okay, right. Now in terms of power, so as we discussed in the previous class, power is the inverse of focal length. P is equal to 1 by F in meters, okay, right. So 1 by F is equal to P, no? 1 by F1 is equal to P1, 1 by F2 is equal to P2, 1 by F3 is equal to P3. So in terms of power, P is equal to P1 plus P2 plus P3 plus dash dash dash, right? And I already told you, and I mean from our last class, here power is positive sometimes and power is negative sometimes, depends upon the nature of lens. So when you are using this expression to calculate the total power in case of combination of lens, we have to take algebraic sum. That is important. We have to take algebraic sum, right? So the algebraic sum of P1, P2, P3, that and all will give us total power, right? Next, combination of lens help us to obtain converging or diverging lenses. Combination of lens help us to obtain converging or diverging lenses of desired magnification. So while starting this topic, combination of thin lenses in contact, I told you. So this is the important application because of this topic, combination of thin lenses in contact, okay, right. And another advantage also he has given, that is enhances sharpness of the image. Enhances sharpness of the image, right? So I think you might have understood the sharpness of the image. Sometimes when we are watching, when we are using either microscope or any other binoculars, right, we are feeling that image is not clear, right? So when the image is clear, the quality is high, right? It leads to, and it is linked to the sharpness of the image, right? So this combination of lenses helps us to increase the sharpness of the image. Next, magnification, right? So what is magnification we know, but here when we are using different lenses in combination, different lenses means number is more, for example 2, 3, 4, that is the meaning of different, okay? They may have different focal length, it is not a problem, right? So when we are using different lenses in combination, what is the final magnification? That is the main important thing, no? So here only we are seeing, say this, combination of lenses help us to obtain converging or diverging lenses of desired magnification, okay? So here total magnification achieved in this combination of lenses, M is equal to M1, M2, M3, M4 like this. So the product of magnification of all those things, right? So M is equal to M1, M2, M3, etc. right? So what I am saying is here, you know very well, in this discussion, the image due to the first lens acts as a object to the second lens. Am I right? Image, suppose here it is I1. So image I1 acts as a virtual object to the second lens. Suppose if you use 3 lens, if you use 4 lens, it continues, right? So finally, when you are going to find the magnification, right? So finally, magnification means it is the ratio of size of the image to the size of the object. There is no change in the basic formula. But here, in this situation, when you want to find the magnification, here M is equal to M1, M2, M3, dash dash. So dash dash means here, suppose if you use 5, M1, M2, M3, M4, M5. Suppose if you use 100, M1, M2, M3, M4, M5, dash dash dash, M100 like that. Okay, ma? Right. Next, such a system of combination of lens is commonly used in designing lenses for cameras, microscopes and telescopes and other optical instruments, right? So such a system of combination of lenses, such a system of combination of lenses is commonly used in designing lenses for cameras, microscopes and telescopes and their optical instruments. So what is the use of camera and what is the use of microscope and what is the use of telescopes? That and all we know in our day-to-day life, okay? And other optical instruments also, right? Okay. So in this class, we concentrated to discuss one example problem based on the previous classes, and next we discuss the important topic, that is combination of thin lenses in contact. So this topic is like 5 more questions or 3 more questions in board point of view. Otherwise, this formula helps us, either this formula and focal power, I mean the total power and total magnification. So these 3 formulas helps us for our competitive exams like NEET and JEE mains. Okay. So this is the derivation when the two lenses are combined for resultant focal length, and it is for resultant power or total power, and it is for total magnification. Okay, ma? Right. So we will continue in the next class.